Imagine, for a moment, the quintessential construction site. You know the scene. You hear the clang of steel, maybe the grind of machinery, workers in hard hats.
Yeah, carefully putting things together, brick by brick, beam by beam.
Exactly. It's a testament to human effort, really, relying on traditional methods and often, a limited set of standard parts.
Right, the catalog approach.
Okay, so hold that image. Now let's contrast it with something, well, pretty different. What if, instead of just assembling those familiar parts, buildings were actually, like, printed?
Or huge sections made by machines.
Yeah, or maybe intricate, totally custom facades put together by robots on site, piece by unique piece with incredible detail.
It's more than just a different picture. It's a fundamental change in what building even means.
Yeah.
That second image, it sounds futuristic, but it's happening fast. It's what people are calling the third digital revolution in construction.
And that's exactly what we're plunging into today. Welcome to the Deep Dive, where we're exploring how that line between the digital plan and the physical building, well, it's getting blurrier all the time.
Faster than you might think.
Our focus today is squarely on the digital fabricators.
Yeah. And our mission in this deep dive is really to give you a shortcut to understanding this cutting edge of construction tech. We're drawing a lot from the work of Neil Gershenfeld at MIT, but also looking at other key sources too.
We're going to unpack how digital fabrication, where basically computer models directly tell machines what physical objects to create, how that's fundamentally reshaping everything, not just what we build.
But how we design it, how we even think about our buildings and cities.
You're going to discover some, frankly, surprising facts and the really profound, sometimes kind of mind-bending implications of this shift. Think about things like 3D printed houses becoming, a normal option.
Or these global networks of fab labs popping up, letting local communities make almost anything they need.
We'll explore the technologies behind it all, the big economic and design shifts towards actual mass customization, not just variations, but truly unique parts, and how these new ways of working are changing the jobs of architects, contractors.
Even skilled craftspeople. Their roles are evolving too.
So get ready for a glimpse into a future where buildings aren't just put together from standard bits, but are truly precisely fabricated, piece by unique custom piece.
Yeah, enabling a level of adaptability and even intelligence we used to only dream about.
Okay, let's unpack this. To really get the scale of this change, we probably need to look back a bit first. Historically, how did we build? The industrial age obviously pushed standardization hard.
Right, mass production.
But even before that, builders were looking for efficiency through repetition, using whatever materials were easily available, weren't they?
Oh, absolutely. If you look way back, way before industrial times, building always had a kind of standardization baked in. It was driven by practicality, what resources you had, the limits of tools, and just, manual labor.
Like the Greek temples. They look unique, but there were patterns.
Exactly.
Yeah.
They're amazing designs. But that standard peristyle, the columns around the main room often had consistent counts, like 6 columns by 14. Sure, the very early ones varied a bit, but there was this clear drive for repeatable, efficient construction using the stone and techniques they had.
So it wasn't mass production like we think of it, but more about consistency within limits.
Precisely. It led naturally to repeated forms because it worked, structurally and practically.
And that wasn't just ancient times. Even someone like Palladio, the Renaissance master, famous for designs based on complex ratios, musical harmonies, even he faced practical limits, right?
Totally. Our sources point out he often used basically rough brickwork with a coating of stucco for a lot of his buildings. The beautiful hand-carved stone. That was saved for the most refined details.
And that wasn't just an aesthetic choice, was it? It was about cost.
Absolutely. It was pragmatic, economics, the scarcity of really skilled stone carvers.
Yeah.
It just pushed things towards simpler, more repeatable elements. It naturally limited how much true customization you could do.
Which highlights this sort of historical tension you mentioned, the practical builders versus the high art architects.
Exactly. For centuries, the builder's utilitarian approach was often kind of looked down on. Sometimes they were called mere mechanics, not capable of grand design. There was this split between the science of building the engineering, the how-to, and the art of architecture.
And usually the simpler, standardized way won out.
More often than not, yeah. It was just more economically viable, less reliant on those rare, super skilled artisans, even if it meant sacrificing some design complexity or bespoke features.
So for ages, the default path was simplify, standardize, repeat. That was the bedrock of how we built. But now we're talking about throwing that whole model out the window.
Pretty much, yeah, a complete upheaval.
This is where it gets really interesting. The digital fabrication revolution. How did we suddenly get the tools to break free from those old constraints?
Well, it's a huge shift, not just a small step. Neil Gershenfeld, who's really central here, calls this the third digital revolution.
Okay, so what were the first two?
The first was communication thing, the internet connecting everyone. The second was computation, the raw processing power driving our digital world. Now he says we're adding fabricating machines into the mix.
So information moving from the digital world.
Right, from the abstract bits on a screen into tangible physical reality. It's not just designing on a computer anymore, it's actually producing directly from it.
So the core idea is computer model data directly controls machines that make physical things. No more manual blueprint reading, no more hand drawing every little piece for someone else to figure out how to make.
Exactly. It bypasses so many traditional steps. And this represents a fundamental move away from that standardization of the industrial age, identical parts rolling off assembly lines, towards an era of mass customization. That's the key phrase, where individual components can be highly tailored, unique, made on demand.
And this is the crucial bit, without the crazy high costs you used to get with anything bespoke or handcrafted.
Precisely. That's the radical departure. Individual design doesn't automatically mean super expensive anymore.
Okay, that really is a game changer. Mass customization at mass market prices. It almost sounds a bit too good to be true. So let's get into the nitty-gritty. How does this actually happen? What are these machines that make almost anything, as Gershenfeld calls them?
Okay, so at the heart of it, you've got technologies like CNC milling and 3D printing. These are really the workhorses.
Right, CNC is subtractive, carving away material.
Exactly. CNC milling uses computer-controlled tools to remove material very precisely. Think multi-axis machines carving complex shapes out of big blocks of wood or metal or even stone for making intricate structural parts, or those bespoke facade elements we talked about.
And 3D printing is the opposite, additive.
Right, building up layer by layer. This lets you create things like optimized internal structures. Think lattices inside concrete beams to make them strong but lighter, or using advanced polymers in ways you just couldn't mold traditionally.
And these aren't just huge industrial machines anymore.
No, that's part of the revolution. In a fab lab, for instance, a small precision tabletop milling machine is a really popular, accessible tool. It brings a complex fabrication down to a much smaller, more democratic scale.
And what about assembly? Are robots putting buildings together? Our sources mention automated manufacturing technologies.
Yeah, while maybe not specifying robots assembling entire houses piece by piece yet in detail, the idea is definitely there. Gershenfeld talks about automated manufacturing technologies driven by data, and even raises this fascinating, almost recursive idea of assemblers assembling assemblers.
Machines making machines.
Exactly, which strongly points towards robots being integrated, not just for making the parts, but for the automated assembly process too, maybe even right there on the construction site. It's about automating the whole chain.
Okay, so the key thing is these machines allow for incredibly customized and complex parts.
Yes, components that would be insanely difficult or take forever, or just be flat out impossible with traditional methods.
But crucially at potentially mass market prices because of the automation.
That's the promise.
Yeah.
It's not just faster, it's different. It opens up a whole new world of design possibilities that were previously locked away due to cost or complexity.
And you mentioned that recursive idea, machines making machines. There's a concrete example from the Fab Labs.
Yeah, it's brilliant. The MTM snap stands for machines that make. It's literally a version of a milling machine that you can actually build inside a fab lab using readily available parts like mass-produced custom motors.
Wow. So the lab can replicate its own tools. That's huge for self-sufficiency and scaling this whole idea up, isn't it? It's almost biological.
It really is. And that recursive capability is kind of the foundation for what Gershenfeld calls the democratic potential of the whole fab lab network. The vision isn't just a few high-tech workshops. It's a global, connected system.
Okay, tell us more about that. What does this democratic potential look like in practice? How does it mess with traditional manufacturing and economics?
It's really about enabling local manufacturing and empowering communities. The core idea is because stuff gets made locally, each product can vary in its specifications based on what that specific community or person actually needs right then.
So give me an example.
Okay, say you're making a simple device locally. Maybe one version needs extra local storage, another needs slightly different graphics. Maybe one needs assistive tech built in for someone specific, or a radio for portability out in the field. You can tailor it right there.
Instead of just picking from 3 standard models made overseas.
Exactly. And doing this locally fosters skills as well as the economic activity of a local investment. It keeps the knowledge, the innovation, the money circulating within the community. It's a different model than relying solely on these massive distant factories and global supply chains. It could redefine self-reliance.
So it's not just about getting a custom thing, it's about building the local capacity to make custom things. That feels like a really big shift. And Gershenfeld sees this scaling,
Right.
like massively, right? 1 trillion fab labs. Seriously.
He does, and the scale he talks about is genuinely mind-boggling. He lays out this progression. First, 1 million fab labs, then 1 billion fab labs, which he calls universal fabrication, meaning they're basically accessible to everyone.
Okay, 1 billion is already huge.
And then, yeah, eventually reaching 1 trillion fab labs. That leads to what he terms ubiquitous digital fabrication, where almost everything is digitally made on demand locally. I mean, 1 trillion.
Yeah.
It's hard to even picture.
Yeah, what does that even look like? Does every house have one, or is it like a utility, a workshop on every corner? What happens to ownership or consumerism? It sounds incredibly decentralizing.
It does. It probably points more towards community hubs, but the tech could definitely shrink down. And yes, it absolutely raises huge questions about ownership, quality control, resource use, intellectual property. If anyone can make anything, how does that work?
Right, that's a big can of worms.
Definitely. But Gershenfeld is clear that the goal isn't just technology for technology's sake. He stresses that the underlying tech and algorithms need to be created with integrated humanistic values. It's not just about churning out more stuff more efficiently.
It's about the purpose behind it.
Exactly. It's about pushing society to advance goals that combine things like sustainability, local resilience, and personal fulfillment, giving people in communities the tools to shape their own world, their own economies, in ways that actually align with their values. It's empowerment through making. That's the deeper idea.
That connection between tech and human values is powerful, moving from just consuming to actually making and shaping. Okay, so for all these complex, customized parts to actually come together properly in a building, you need a central brain, right? A digital hub coordinating everything.
Absolutely. And that's where building information modeling, or BIM, becomes totally essential. It's the digital backbone for this whole shift.
It basically replaces the old stacks of blueprints.
In a way, yes, but it's much more than just a 3D picture. It completely changes how teams collaborate. Think about trying to coordinate traditional 2D drawings between architects, structural engineers, mechanical engineers.
It must be a nightmare. Constant cross-referencing, updates everywhere.
You got it. Our sources say BIM tech facilitates simultaneous work by multiple design disciplines. That's a massive leap. Traditional drawings are inherently more difficult and time-consuming for collaboration and just ripe for errors and misinterpretations.
But with BIM, everyone's looking at the same coordinated 3D model.
Essentially, yes. One or more coordinated 3D models where changes are tracked meticulously. This radically shortens the design time and significantly reduces design errors and omissions because you spot conflicts digitally, way before they become expensive physical problems on the building site.
So it's faster, but also catches mistakes earlier. That must save a fortune.
Huge impact, yeah. BIM gives teams earlier insight into design problems. It lets designs be continuously improved throughout the process. It's much more cost-effective than the old way, where you might only do value engineering after big decisions are already made and changes cost a bomb.
It's like optimizing as you go instead of fixing things afterwards.
Exactly. Iterative optimization versus retrospective correction.
And BIM is really the state-of-the-art for this parametric modeling idea, where changing one thing updates related things automatically. Like, if the architect moves a wall,
the model knows the pipes and wires in that wall need to adjust too. That's the core concept. BIM is the current state of art in parametric modeling. It means parameters defining shapes could be automatically reevaluated and the shape rebuilt when something changes.
How smart is it?
Pretty smart. The software often has a resolver capability. It analyzes the ripple effect of a change and updates all the dependent bits efficiently. It keeps the whole complex model consistent, like a single interconnected digital thing.
Okay, but you've got all these different companies, different specialists using different software. Architects use one thing, engineers another. How do these systems actually talk to each other without messing up the data?
That's a critical piece. Open standards. BIM relies heavily on public product data model exchange formats. Things like IFC Industry Foundation classes, CIS2, ISO 15129-6.
These aren't owned by one company.
No, they're open. They often use open languages like XML to share not just the 3D geometry, but also connectivity data, material properties, even cost info across different software. This openness is absolutely vital for collaboration across the whole construction ecosystem. Everyone can work on the same virtual building, using their preferred tools, and trust the data.
Okay, so BIM makes design and collaboration smoother, faster, more accurate, but it also directly impacts the actual production of the building and the cost, right? Beyond just the design phase.
Oh, massively. BIM enables what people call virtual construction. You build the whole thing digitally first, coordinating among all building systems prior to producing each piece.
Like a digital dress rehearsal?
Exactly. You're essentially building it component by component in the computer before anything physical gets made or delivered. This is especially huge for what they call engineer-to-order, or ETO components.
The really custom stuff.
Yeah, bespoke facade panels, complex structural joints, things that need sophisticated engineering and careful collaboration to fit perfectly. BIM lets you iron out all the kinks virtually, avoiding expensive rework on site.
I can see that, like catching a pipe that's supposed to go right through a main beam before either gets made. That clash detection example you mentioned earlier sounds like it prevents exactly that kind of expensive headache.
It really does. And that virtual build process significantly reduces the time required to generate shop drawings and material takeoffs for procurement. That's a huge bottleneck usually.
Meaning you can make changes later in the game.
Yes, late design changes can be accommodated later in the process than is possible in standard 2D CAD practice. Because when you change the central BIM model, the updated erection and shop drawings are produced almost automatically. It saves enormous amounts of time and tightens up schedules.
Which must help with cost control, too. Does it make estimating more accurate?
Definitely. BIM greatly facilitates the development of interim estimates. Designers, owners, they can see budget problems emerging much earlier and make more informed decisions about design choices that affect the cost. It supports model-based budgeting and estimating, allowing for proper options analysis and value engineering right from the start. It links design directly to cost in real time.
Proactive financial management, not just hoping it comes in on budget at the end.
Exactly. Avoids nasty surprises.
And that Navisworks example really drives it home, doesn't it? Using the model as the main interface between all the different subcontractors.
Yeah, it's a powerful case study. They integrated various models, likely from different software, into one Navisworks model. This allowed for early conflict and clash detection.
And they found real problems.
Oh, yeah. Potential clashes between mechanical systems and the existing structure. Things that would have been very expensive to solve during the construction phase. Catching those early allowed the team to be proactive during the design phase instead of reactive during the construction. It completely changed the risk profile. As they put it, you get what you want early on rather than living with problems later.
That's such a clear benefit, proactive versus reactive. It shows BIM isn't just a fancy drawing tool, it's a core management platform. And speaking of the final building, this whole digital shift isn't just changing how we build, but also the kinds of buildings we'll live and work in. They're becoming more dynamic, more adaptive.
Absolutely. The lines between the digital and physical are just blurring everywhere in our environment now. Think about cities. They're increasingly packed with sensors collecting data traffic, air quality, energy use, you name it.
And then actuators responding to that data.
Exactly. Network-enabled actuators can transform spaces based on that info. This creates these complex, data-driven feedback loops. It basically turns the city itself into a reflexive testbed and workshop for connected habitation.
So the city isn't just static concrete and steel anymore. It's sensing, responding, almost like it's alive.
In a way, yeah. It's a huge leap from traditional urban planning.
Yeah.
It sounds like sci-fi, but it's happening now. We're moving towards programmable architecture and truly dynamic spaces.
Like what? What could that actually look like?
Imagine a building facade that changes its shading or transparency automatically based on the sun's position and whether people are inside, optimizing energy use. Or maybe even internal walls that could physically shift to reconfigure a space for different uses throughout the day. Adaptable, responsive environments.
And the buildings themselves become intelligent agents. What does that mean for us inside them? Is my house going to start arguing with me?
Huh. Probably not arguing, but definitely responding. Sensor networks, combined with AI or machine learning, can transform buildings into intelligent agents with the capacity to learn from and coexist with their occupants.
So it's moving from living in a home to living with a home.
That's the phrase, yeah.
Yeah.
It fulfills this long-held dream of dynamic spaces. Architecture becomes less of a fixed shell and more like a form of interface, connecting the digital world of bits and the physical world of atoms.
So my home could learn my habits, adjust temperature, lighting.
Exactly. Anticipate your needs, learn your preferences, optimize comfort and energy use automatically. It's like a continuous, subtle dialogue between you and your living space.
That's a wild thought, living with your home. But for buildings to be truly dynamic like that, constantly adapting, they need to be designed differently from the start, right? We usually build things to be permanent, solid.
That's a crucial point. It brings in this concept of slivage. Buildings need to be designed to allow slippage between the differently paced systems. Think of a building having layers that age or change at different speeds.
What kind of layers?
The framework often mentioned is site, which is permanent, structure, very long-lasting, skin, facades, maybe last decades, services, electrical plumbing, HVAC changes faster, space plan, internal walls might change often, and stuff, furniture changes constantly.
Okay, so the idea is the slow layers shouldn't block changes in the fast layers.
Exactly. Slow systems shouldn't block quick ones, and quick ones shouldn't require tearing up the slow, expensive ones. This is vital for long-term viability.
Especially with technology changing so fast, services seem like a key area here.
For sure. Services such as electricity and gas are driven constantly toward greater efficiency by their sheer expense. Plus, the march of technology is inexorable and accelerating. Think how often we upgrade our Wi-Fi or kitchen appliances, or even HVAC systems become outdated.
Yeah, kitchen and bathroom renovations are constant.
Right. That constant turnover in services demands building designs that make changes easy, not destructive and costly. Digital fabrication can really help here, making it easier to design for modularity and replaceability.
There's that interesting historical comparison, too.
Yeah, apparently in Maryland, you can find more intact houses from the 1700s than you can find pre-1920 toilets. It just shows how much faster the service layers churn compared to the basic structure. We need to design for that difference in pace.
That's a great illustration, designing for adaptability, for different layers of change. It's not about building something static forever, but something that can evolve.
Right.
Which leads us to the people involved. What does all this digital fabrication, BIM, adaptive building, what does it mean for the actual humans? Architects, contractors, craftspeople, their roles must be shifting dramatically.
Oh, completely. It forces everyone to rethink traditional roles and skills. Take architects. Traditionally, many focused on designing, little gems of new buildings, these iconic standalone projects.
Signature building.
But now the call is to retool, to get new kinds of knowledge, skills, and attitudes. There's a much bigger emphasis on renovation, adaptive reuse, and especially sustainable design. The focus is broadening from just the initial form to the entire life cycle, how the building performs and adapts over time.
So less focus purely on aesthetics, more on performance, function, flexibility. And digital fabrication lets them actually achieve designs that reflect that, rather than being forced into simpler shapes by old construction limits.
It absolutely does. It frees them from constraints that maybe led to awkward compromises in the past, like those symmetrical equiponderant facades that didn't always work well with the domestic arrangements inside.
Function following form, sometimes badly.
Right. Now, design can be directly driven by function. User needs, how it performs environmentally, material efficiency, echoing that old Greek idea where the structure and purpose are clear in the form itself. Parametric design in BIM lets them explore incredibly complex, non-standard shapes. Parametrically designed building facades that respond to sun angles or views or structural loads. It's way beyond just aesthetics. It's about high-performing responsive architecture that can actually be built affordably now.
That is a huge shift. Okay, what about the contractors, the construction managers? Their world must be changing from coordinating muddy boots on site to managing something more like a high-tech manufacturing process.
Very much so. Digital fabrication pushes things like improved pre-assembly and prefabrication. Think of precast concrete. That's an early version, right? Components cast and cured in a place other than their final location, then shipped for assembly.
So less work happens physically on the site.
Less raw fabrication, yes. It becomes more about orchestrating the precise assembly of these complex, often custom pre-made components. It changes site management fundamentally.
Demanding a more proactive, digitally savvy approach from the construction manager, I bet. Less reactive firefighting.
Exactly. CMs are increasingly using BIM for things like virtual hard-at reviews. They walk through the job site logistics digitally, run that clash detection we talked about, all before anything physical happens.
Mm.
It shifts the whole process from discovering problems on site, which causes delays and costs a fortune, to proactive prevention in the digital realm, solving problems before they happen, or rather, when they happen virtually, which is much, much cheaper.
It sounds like the industry is really moving from being seen as maybe mechanical work to something much more scientific and data-driven, like optimizing a factory line.
That's a great analogy. That old schism between the science of building and the art of architecture is definitely blurring. Techniques from manufacturing optimization, like applying the theory of constraints, TOC, for finding bottlenecks, which was developed for the design of new plants and production lines, that kind of thinking is now being used to solve problems before they arise in construction. It's becoming a highly engineered process.
So what are some of these new best practices CMs are using with these digital tools?
Well, it involves much more sophisticated planning and monitoring compliance with the project timeline. And really crucially, obtaining commitment from each contractor to hit those targets within that digital framework. The tools allow for much better progress tracking, resource management, handling schedule revisions dynamically. It's all about data-driven coordination and accountability to a degree that just wasn't possible before.
Okay, sounds super efficient, highly controlled, great for delivering projects. But what about craftsmanship, the human touch, the skilled artisan? Does that just disappear in a world of robots and digital models?
That's such an important question. And the answer seems to be no, it doesn't disappear, but it absolutely redefines itself. Craftsmanship isn't lost, but it evolves.
How so?
Well, think about historical craft. Incredibly detailed wood joinery, maybe interlocking wood-to-wood connections, needing no nails, or how wood shingles were woven at the corners perfectly. That was precision achieved through immense manual skill and deep material knowledge.
And now that precision comes from the digital model and the machine.
Largely, yes. The precision shifts from the hand to the programming and the setup. So the craftsperson's role changes. Maybe less hand shaping, more overseeing and refining what the machine produces, ensuring the quality is perfect. Or perhaps they become the experts designing the complex digital models for the machines.
So it's a different kind of mastery, more intellectual maybe, managing the technology?
Exactly. It's moving from pure hands-on making to intelligent design, skilled operation, quality control of advanced tools, the meticulous eye, the understanding of materials. Those are still crucial. But how they're applied changes.
That makes sense. It's a transformation, not an elimination. And the Fab Labs connect back to this too, right? Empowering a new kind of digital craft.
Absolutely. By making advanced tools accessible locally, Fab Labs ensure that makers gain the skills as well as the economic activity of a local investment. It fosters this new breed of digitally empowered craftspeople, people who can design and produce sophisticated, customized goods right there in their own communities. It sort of revitalizes local making, creating digital artisans.
Wow, what an incredible journey we've taken just now. From ancient temples using standard forms and sheer human effort
Through the whole industrial age of mass production.
to a potential future where our homes are smart, adaptive partners, custom made by machines we might have even made ourselves in a local lab.
It's quite a leap. We've seen how digital fabrication, driven by people like Neil Gershenfeld and powered by tools like BIM and the Fab Lab network, is really pushing construction into this new era. Unprecedented customization, efficiency, even intelligence baked into the buildings themselves.
Yeah, it's a profound shift. From just assembling standard pieces to precisely manufacturing every part, often on demand for unique needs, it really changes our whole relationship with the built environment.
Makes it far more responsive, more adaptable.
So for you listening, whether you're involved in building, planning a renovation, or just curious about where all this is heading, this deep dive hopefully shows that the spaces around us are poised to become way more dynamic, smarter, and more attuned to our needs than we've ever experienced before.
We're moving into a time where our buildings aren't just passive shells, they're becoming active, potentially learning participants in our daily lives, capable of evolving alongside us.
Which leaves us with a final provocative thought to chew on.
Okay.
If buildings are becoming these intelligent agents learning from us, coexisting with us, and if machines can, in fact, make other machines, what completely new forms of life maybe could our built environments develop? Things we can't even imagine right now.
What unexpected relationships might emerge between us and these programmable spaces?
Exactly. And how will our own lives, our sense of comfort, our privacy, how we interact with each other and our surroundings, how will all that change as we move from just living in our homes to truly living with these digitally fabricated, potentially sentient environments? It's a future that needs more than just new tech.
It needs new ways of thinking about our place within it all.